Okay. It is a great pleasure to announce today's speaker, Luke Davis, who will talk about controlling discrete and continuous state non-equilibrium systems.
Okay, yeah, thank you, Kadina, and yeah, thanks for everyone for turning up. And yeah, it's a pleasure to speak in the SSD program, which has been great so far. So I'm a physicist by training. I don't know actually how many people are mathematicians, physicists, but I'm really going to approach this as a theoretical physicist, and hopefully I'll speak some of the language that is familiar to mathematicians. So it's always good to actually talk about what's in the title, maybe to define things that maybe you're not familiar with. So discrete and continuous, you might have a nice feeling about what those words mean. But non-equilibrium systems, okay, that might be a bit different. So in physics, there's a framework called statistical mechanics, which basically wants to relate microscopic observables of systems of many particles to more macroscopic observables. And these normally have a thermodynamic flavor, things like pressure, free energy, temperature, and so on. And typically, systems at equilibrium obey, they occupy states that are given by the Boltzmann distribution. So something like this. Let me know if you can't see this. So this should be bread and butter for some and looks familiar for others. So this is the Boltzmann equation. So the probability to be in some state is just weighted by exponential minus beta times the energy. Beta is just 1 over kBt. T is the temperature. Kb is Boltzmann's constant. Okay. And Z is something called the partition function, which you all know is just the sum of all the states a system can be in. So at thermal equilibrium, all states are weighted like this. So non-equilibrium, so deviations from this, the probability to be in some state does not obey this equation. So non-equilibrium means non-universality of the Boltzmann distribution. And there's also something related, not exactly the same, but related, that if you have some, I'm being quite general and maybe a bit vague, if you have some time-dependent function, now, okay, I'm being very vague, it's not exactly how it is, but if I basically reverse time, the functions, you can tell no difference between the functions. And out of equilibrium, you would tend to have something called time irreversibility. Okay, so that's just to kind of give you a flavor of what non-equilibrium actually means. So in these systems, I mean, I can take a system at thermal equilibrium and I can push it, right? I can poke it, I can throw it, heat it up, such that it, when I externally fiddle around with the system, it's out of equilibrium. And then if I let go, if I stop driving the system, it goes back to passive. When I say passive, it's synonymous with equilibrium systems. But there are some systems where even if I'm not meddling in their behavior, so I'm just letting them be, they still persist far away from equilibrium. Now, such systems are called active matter. So active matter consists of individual constituents that produce entropy. And when you put lots of these particles together, they interact. And this often results in phenomenology that's not seen in systems at equilibrium. Okay, so I didn't talk about entropy, but we know that, okay, we might have heard and be very familiar with the Boltzmann's, well, the second law of thermodynamics. And in general, if you look at a particle in a gas at equilibrium, it's not producing entropy, right? So that's another thing to think about is entropy production. The entropy we normally say is S. if I look at the exact time derivative of entropy, in equilibrium, this is 0. And you can look at individual particles. The individual particles, you can say, are you producing entropy? Okay. In active matter, this is positive. So that's what it means. Yeah. So this is, okay, yeah, I've already fallen into a trap where entropy is normally taken for a large system, right? But there are ways to think about local entropy production. So you can, on the local level, think about, okay, well, I mean, you've ate some lunch. In order to move and do some, I would say you're out of equilibrium. I mean, the temperature of you is higher than the environment, otherwise you'd be dead. So I think on the level of you, which is a constituent of the system, you're producing entropy. So you can think of it like that.
Expectation over a subset of the entire system.
Probably not so much like that. I think it's just more that, in your system, the constituents themselves are burning fuel, and then that's out of equilibrium. So in nature, I don't know if you've had the pleasure of seeing a flock of starlings. So, it's a beautiful phenomenon where many starlings move as a collective. And the key physical point is that there's no leader. So normally a man in a pub will be like, who's the leader bird? Who's the leader guy? There's none. So we move as a collective without a leader. And this actually is, you cannot get this behavior in a passive system. Okay? So you can get phenomenology, collective, many-body behavior that with passive ingredients you just would never see. Okay, so it's interesting. Another interesting thing is that you can also have man-made active matter. So this is on the microscopic level, so literally 10 to the minus 6 meters. If you can see, particles are accumulating and they're forming these little clusters, highly ordered clusters. And you probably can't see, but they're soaked in a bath, a vapor phase of other particles. So these particles are literally spheres, and they're covered in a chemical, okay, whereby if you shine photons, this actually causes a chemical reaction, which leads to a propulsion-like mechanism. So these colloids can propel in a certain direction. Yeah.
So, for example, if you have a fluid, let's say
Mhm.
you see either one big whirlpool or many smaller whirlpools in it. Isn't it something like that?
Out of
in this
but you're saying that if I see like a whirlpool, I'm seeing lots of water molecules moving almost collectively, right? I would say that's not the same thing because, in a sense, I mean, birds are stupid, but not as stupid as water molecules, right? And you're driving the water, right? Here, the system, the fact that the birds are themselves out of equilibrium and they come together leads to this collective behavior. So I would say in your case, the whirlpool of water is a driven passive system. So, but it's good to make analogies with that actually. So one thing that here is if you shine light, they form clusters, and when the light is off, you regain equilibrium behavior. What I mean by that is that if you wait long enough, the light is switched off, and the particles move in a Brownian way. So they undergo Brownian, like random walks. So Brownian diffusion. So this is now not anomalous diffusion, right? So the interesting thing about these particles forming clusters, which you can see here, is that they're not sticky. There's no cohesion. So just by the mere fact that particles have some persistence in some direction, like they have some persistence, okay, they get moved by fluctuations in some other way, but they have some finite persistence, and the fact that they take up space, so they have volume exclusion, means that they form these clusters. So if two particles bump heads, so this guy is going this way, and this guy is going that way, because they have some persistence, they will stay together for some time. Now you can imagine that if I have a solution of a sufficient density, if two guys stay for a little bit, a third guy comes, a fourth guy comes, and so on. So that's sort of how the clusters form. But the interesting thing is that there's no cohesion. So this is, again, really an active phenomenon. Okay, so if you're familiar with active matter, this is really the basic stuff. But if you're not, hopefully I've given you a flavor of that. You can see interesting physical behavior that you just will not see with passive ingredients. Okay. Well, right, okay. Active systems are funky. They do different things. So what? Okay, it's beautiful. Well, now with some big vision that actually we might be able to manipulate and control active systems in order to make new technology, essentially. We can also make technology that can interact with biology, make new engines based on active ingredients. So maybe we can hijack the functionalities of active matter to create new technology that surpasses passive machinery. And this is kind of giving you just a very brief overview of what controlling active matter has been like in the past decade. It's a very, I guess, new subfield of active systems. So for instance, some bacteria, if you let them roll around in the dish, they exhibit turbulence on length scales that you would not see in usual fluids. And there's some motivation to control the vortices in this fluid. Controlling, so there's something called mass transport, so an optimal transport. That's a very systematic area of mathematics and physics. You can apply the same tools and same ideas for active drops, and you can actually gain a deeper insight into passive systems as well. And you can also think about controlling individual constituents and maybe going back to the old ideas in thermodynamics about pistons and engines and so on. And this is just some selected references. Yeah.
So going back to when you have the motility-induced phase.
Yes.
So those particles, when the light hits them, are we picturing this as when the light hits from these particles, they then have a bias in some random direction?
Yeah, but they have, so particles move. Let's just say I have a normal particle and I wash away the chemical. It will move because it's being buffeted by other particles. Now, with this mechanism, they have just, they stay in some direction for a little bit longer than in the Brownian case.
And that direction is
that direction is random. But that coupled with excluded volume is sufficient to get phase separation, which is very non-trivial. Okay, so that's some background. So I'll just have some time again on some background, and then I'll go into some deeper things. Of course, when I'm manipulating system, I mean, I can create this simple diagram. Okay, the physics can be continuous or discrete. So continuous just means that, for instance, a particle, it can move around smoothly in the space, right? Like I'm doing now. My position is a continuous variable in this plane that is the room. And therefore the energy states are also continuous, okay? But I can also hop, right? Imagine there's like a hopscotch. I can also hop and if there's energy associated with that hopping, then I'm in a discrete physics, okay? And the control can also be the same. I can smoothly move a knob. Like on the radiator, there's a smooth little knob that I can tune, but it also can be a switch. Okay, this is probably pretty trivial, but today I'm just really going to be focused on continuous control, but the physics is continuous and discrete. Okay, so let's talk about optimal control. So optimal control is an established field in applied math, and essentially from a physicist's summary, it's really to go from one point in some phase space of your system to another point in a way that optimizes an objective function, okay? So an objective function generally looks like something like this. So people call J the optimal objective function J, and it usually can be massaged into a form like this. So you have a boundary term, B, that depends on your protocol. Now, let me tell you what alphas are. Okay, so let's just say this is a fake diagram. It's just blue in the top left and orange in the bottom right. Let's just say I have some physics that's different in the different colors, and I want to go from top left to bottom right. I mean, there's many ways to do that, many trajectories. Let's just say, and actually this is a very let's just say, that there is one unique trajectory that optimizes this J. Now, but what is this trajectory? Let's just say, like the radiator, this is alpha, okay? It's one control parameter. It's like probably how much current is going to the coils to heat up the room. So you can imagine alpha is just the value of the heater. Now the boundary term depends on the starting value of alpha and the final one, and potentially the speed, the rate at which you're changing the knob. Now X, underlined X, is just the state of the system at the beginning of your protocol and the end, the final one. Now the interesting one, so optimal control theorists call this the last term, the second term, the running cost. Physicists would like to see this as an action, hence I've put a Lagrangian inside. And it's essentially that. You want to extremize this second term in order to minimize J. So this second term is normally where all the richness of the problem lies. And the integrand is some L, as some Lagrangian, that depends on your control value and your control velocity. Of course, you can have you can control many things at once, but let's just focus on one alpha. And of course, it depends on the state of the system at some time t. So this is just the general cost function here. Okay. So in order to control something, as a physicist, we like to think in perturbations. I watch a system, I prod it with my finger, or foot, depending on how you feel, and I see how it goes, right? If I understand, if I can quantify the response of the system, I can control it. I can begin to think about controlling it in an optimal sense. But first, I need a basic model of the physics. So I have to corner myself a little bit. So what I'm going to consider is overdamped Langevin dynamics. So you can imagine these particles, they actually have a mass, but their mass doesn't matter because they're in a viscous fluid. If I make this assumption, I can write the particle velocity, which is this r dot I, as a sum of two terms. The first term is basically a mobility, mu, times a force. The first term of the force is the familiar one. It's just the conservative force. It's the conservative force, right? Minus the derivative of a potential energy. And then there's the second term in the force, which is self-propulsion. So VI, it is a velocity. It's basically, it's a particle propelling itself because it's burning food. The last term on the left-hand side is thermal noise. So D is a translational diffusion coefficient, eta is a Gaussian white noise with unit variance and so on. So people from stochastic background, I mean, this should be quite familiar. If V is 0, I have Brownian motion under some potential. If F is 0, I just have a random walk. Okay, given this dynamics, I can think about an action. Yeah, tell me. The V actually is another stochastic random variable that obeys another law that I haven't yet specified.
Does it change over time?
It does change over time. Yeah, V changes over time. And the main thing is you can think about V as, so VI is a vector, but usually what people think is some scalar, some magnitude, times some orientation. So E hat is just where I'm facing, and it's just, I'm going at some constant speed. That's usually, but the orientation is changing. That's, yeah, exactly. You can link it to the particle. So with this dynamics, I have an action. So in physics, in case you might think, okay, what the hell is an action? An action is a nice, elegant approach to classical mechanics where if you trajectories of your system, they want to minimize the action. So it's Fermat's principle of least action. Okay, so it's probably good to think about in this context. So the action is given explicitly like this. But I have two sources of stochasticity in my system. I have the thermal noise, eta, the eta term, and I have the active noise, okay? So I have to probably think about averaging over realizations of noise, okay? So this is what I mean. So if I have some observable x, its ensemble average is just given by this. Some normalization, which at equilibrium is exactly 1 over z in equilibrium. And basically, this observable weighted by e to the minus s, and this measure is just telling you for some thermal noise path and some active noise path. So this is from the path integral formalism, and these are just things. But basically, this is what the ensemble average looks like. And I need this to specify the response. Because when I think about the response, how something responds, if I turn the radiator, I want to know how it will respond for all realizations of the noise. It's about robustness. That's just the intuitive view. Okay. So let's stick with some observable x. Now, I prod it, right? I prod this system and I measure x. Now let's just say that this prod is, I'm prodding it very slowly and very weakly. Okay? That means I can expand an observable to some order and stop. So the first term is x at the steady state. If I'm not prodding, x has this value. The second term is the linear response. To some linear order, it responds to my prodding like this. And then the third term is the second order term. Now, usually physicists working on controlling equilibrium systems stop at the linear term because that's sufficient to do what you want. It just so happens that we need the second order term for mathematical consistency when dealing with active systems. So it's not that I started working, here's the action, oh, I need the second order term, of course. I started with just a linear response and I worked out that I was wrong mathematically because I didn't have this. But that was a sort of nice insight that already with active systems, you have to go to second order. Already, that's something different from passive systems. We've learned a lesson already. Okay, this is just for your reference. Okay, so this is what an expansion looks like. Yeah, tell me. Ah, yes, good, sorry. So who is delta alpha? Delta alpha is the perturbation. So it's my finger prodding, but it's this radiator. It's the perturbation. Okay. delta the radiator setting.
From time t to time t.
Exactly, from time t. And there's usual time ordering, so t prime is greater than t. And in the second order response, t prime prime is greater than t prime, and so on. So,
You need this second order because the things that you measure in the second derivative. Is that what it will?
it's a good question. It's not as simple as that. But that's also what I thought. It's essentially that when you're invoking a self-propulsion in the objective function, you have 1 over t appearing where you didn't before. So 1 over t, that means, so t is like a current time. Exactly. So, okay.
Sorry to interrupt.
No, it's okay.
In linear response, you usually cover the first term. Oh yeah, here we go. Yeah, because
Sorry,
usually
yeah.
the first derivative start, you take the limit out and go. Okay. But yeah, the reason in linear response, it's because you're interested in first derivative. Your probably gets to 0.
Yeah, actually, so what Michael's saying is actually it's good actually because in some sense with the objective function I'm going to expand it, right? That's what I'm going to do, as you can probably tell. And actually I want to expand this objective function to linear order. But in the total time it takes for me to control. In order for me to do that in a consistent way, I have to go to second order in the expansion of these observables because of the activity. So it's quite subtle, actually. So this is just by definition, right? As I showed you before, this is what the responses look like. And then the bottom is actually the explicit relations between responses and functional derivatives of the observable. So I'm using the definition of the average of x. Now, in some literature, so it's nice to have these clear formulas because these n's are important. So maybe when you've worked with stochastic differentiation, or in physicists, if you worked in quantum field theory, you know that if I take functional derivatives of e to the minus s, I'm going to get correlation functions, but they're going to be unconnected. So let me, I can show what they mean, but unconnected correlation functions means that I'm looking at correlations and not covariances. So physics language, connected correlation function just means a covariance, where you know at some long time, if I go on the x-axis far enough, a covariance should go to 0, right? And in order for that to happen, you need to have this normalization factor. Okay, it might be trivial to some, but you have to be careful with this. And because, okay, I'm just letting you know all the details, but in the objective function, I need to take indefinite integrals of these responses, and they have to converge. So if you don't have this n, you don't have convergent integrals. So in physics, the integration of a response is a susceptibility. So if you know about susceptibilities, you understand a bit of this. Okay, so let me march on. So this is just algebra, right? You plug in, you just do the math. And I'm just telling you what I just said, that you get connected functions. I get a correlation, a 2-point function, minus the product of the averages, which is the covariance. So this double bracket just means I'm looking at the connected correlation function. So already this is what the linear response looks like, but I have to actually differentiate the action. And after some massaging, this is what the linear response looks like. And this agrees with some more general formulas that are found in the statistical mechanics literature by Christian Mays, Erna Basu, and so on. But this is really explicit, so this is a final expression. Now, this is just what derivative of the action looks like. Okay, so I'm sort of walking you through this quite slowly. Okay, so we have this linear response. And you can see the first term looks sort of usual. I have the observable times some gradient of the potential. And then I have the second term contains details of the activity. So F contains V and so on. Now, you remember what I said about time irreversibility in active systems? Well, if I switch activity off, I know I should get something that is in textbooks, right? And indeed, if I switch activity off, I regain time reversibility. So if in physics, we do something called symmetrizing equations, symmetrizing a response. If I take the response and minus the response with the times flipped, swapped over, I get this, and some terms will cancel, and I get the well-known fluctuation dissipation theorem. So this is the Kubo relation. Okay. So okay, we're on safe ground. So this linear response formula is correct in the passive limit. Okay, I won't explain this equation, but the thing is we can get a closed form expression for the second order response, and it's all, it's doing the same thing. So it's systematic. You can put it in Mathematica and it will press go, and it will give you this with some tidying up. It contains some double derivatives. Okay, but it has some form that's long, but it's closed and it's computable. And it only depends on correlation functions. The second order response depends on 3-point connector correlation functions. Okay, and this actually is a more general form of some formulas in the physics literature, in the condensed matter literature. This is just some definitions of what the 3-point, and if the stats people will recognize this as the kurtosis, skewness. This is skewness, so it's all, and you can get the kurtosis and so on. Okay, so in order to control something, I wanted to know how a system responds weakly. And I have a handle on that, right? I have a firm handle on the responses. So, I mean, as a physicist, I feel a bit more confident about I can actually now start thinking about controlling systems ultimately, irrespective of any objective function, right? I didn't tell you what objective function I'm dealing with, just the, Now, this is for continuous systems. Now, this framework, this formalism, also extends quite naturally to discrete state systems. Now, what do I mean by discrete state? Again, on the top left, I have some energy against time. Now, as the time goes forward, the system jumps between energy levels. And let one particular trajectory be omega O, comma F. Omega is just some particular trajectory of the system. Okay, a good starting point to look at the dynamics of this system is the master equation. So in the master equation, we have the time derivative of the probability of being in state I is just the sum of products of transition rates. So Kij is just the transition rate to leave J and enter I. So all the states, the probability of being in some state is in some state I, and this is J, and this is K, and so on, maybe. It's just the eagerness of going from all the other states into state I. Okay, that's what the master equation says. Now, Kij is a particular choice of the transition rates. The physicists, I don't know, I say it's Arrhenius form. What would you say? Arrhenius? Yeah. Well, Alessandro read it.
CIJ.
It also depends on your Cij, exactly. So in this form, it's like, a chemist will probably recognize it. It's like the law of mass action. This form guarantees thermodynamic consistency. Why? Because, so epsilon here is the driving. So in the continuous state, I had V, which is the propulsion. Epsilon is like a bias to a particular energy state. So it's like bias, it's like a active persistence. Now, if epsilon is off, I have an equilibrium system, and the transition rates is just depends on the difference between the energies of the two states. Okay, and only with these rates can I get something called detailed balance. So detailed balance means it's the same as having an ergodic system that there's no difference between forward trajectories and backward trajectories. Okay, yes, Toby.
Bias, the epsilon ijector,
Yeah.
they tend to be non-zero only for neighbouring. You wouldn't bias towards something really far away. It's like to encourage quick hopping.
Yeah, yes. This is a good question. So here I really only can neighboring energy states, which actually makes sense. Like okay, if I want to go all the way up the stairs, I have to climb each step. But it's a good question. You might be able to teleport. Yeah, you can add that structure in. Oh. What? Yeah, you can definitely do. You can have well, you can assume some decay, right? You can add a decay that.
When you can jump between, you don't need to go step by step on an airplane.
Yes, you can. I mean, even in with the classic the electron states, right? You can suck a photon of enough energy. You can go all the way out, right? That's an interesting question. I don't know, Alessandro, maybe an active system. Yeah.
It depends on your interaction network, basically.
Mm.
You have fully connected easing or discrete model, yeah. But then in this case, also the energy level, one operation at a time.
Yeah. It's still discrete. It's still jumpy. Yeah. Yeah. So. I think maybe relating to the quantum, but not quantum, is strongly correlated systems.
Yeah.
Where the correlation length spans some scale. Oh yeah, that's true. Phase transitions I haven't mentioned yet, but that's interesting actually. I didn't think about it. Okay, okay, very good. So like I did in the continuous state, so I'm not doing anything fancy. I worked it out in the continuous state system. I roll out the same thing in a discrete. I'm not doing anything more fancy than that. So I need to define the ensemble average, and this is what it is, actually. This is trivial. And then I need to know the time derivative of this. Okay, I had the continuous action. Now I have a discrete action, which is exact. So this is quite subtle, actually. So K bar is some reference transition rate, which actually falls away when you take derivatives. We need it there for, consistency and units. But it goes away. But we had to put it in there. And these things are just very compact ways of keeping track of jump times on trajectories, okay? Okay, so, yes, yeah, tell me. Yes.
Is KJI?
No. Not necessarily. It can be more general than that. So K bar, it just needs to be a reference transition rate. Yeah.
Which is related.
So it's not simply the swap in the indices, because I mean that is another reference transition rate, and that would be fine. But it can be any reference one.
It's like K1, 2.
It can be 1, 2. It could be any.
There's not one for each pair I get. It's one for the whole.
Yeah. Yes. Yeah. I think there's a. Yeah. Maybe. Oh, yeah. That's a good point.
I mean, you have this logarithm problem whenever
You're counting.
Yeah.
Yeah. Yeah. So this is. I mean, there's no approximations in this. This is this is exact, but I think, yeah, we needed the reference one because essentially when you look at probabilities, okay,
So maybe in the calculations it just falls out.
it falls out, but actually you're right in the sense that even in equilibrium, the reference is Z in some sense. And in this case, you can think of that as yeah. Oh, what, sorry?
You introduce and then
Yes, okay, actually I didn't think about it in gauge, but that's essentially is. It's a gauge that the physics doesn't depend on it, but you need it in the equation and then it falls out. Yeah, so this, we needed it. I don't know if there's anything deep in there. Are you?
You only had a log Kij, so you needed a Kij log.
Yes, I needed it, yes, exactly. But then we realized, we first were like, is it just the swapping indices? And I was speaking with Corel about this, and I wasn't entirely sure that it needed to be that, actually. So maybe then we just generalized it. Yeah. Yes, omega is a trajectory. I go from A to B. Omega is just some particular trajectory. It's an instance of like a configuration in continuous time. Yes, and gamma is a labeling of how many times. It's the list of times that you've entered, that you've jumped. It's a way of counting it to keep the books clean. Nothing interesting physically, but. Okay, I can speed up. So basically, you get the same form of equations as a continuous case. That's the main thing, is that nothing is more different in a discrete case. Of course, the specific equation, there's transition rates, but the form of the equations remain the same. Which is good because it means that, now the framework, you can just roll it out for a wide range of different physics. Okay, so yeah, I wanted actually to spend more time on the building up of the framework to kind of give you some insights, however useful or trivial. But I've missed something in the talk, right? The main thing, active matter is cool. It can do some cool things. If we manipulate it, maybe we can make it do better, the cooler things that we want it to do. But can't we just use the same physics that we know for passive systems and active systems? Reviewer number 2, this is just, you're calling this another name for something that's already been done. Well, in some cases, and actually, that's not true, basically. So what we know about active systems is that they're producing entropy, so they're heating up the system. They're heating everything up. Now, if I control a passive system and I look at the heat dissipated to the environment as a function of how long it takes for me to control it, TP is like I'm being really, really slow. We know that the most efficient protocol duration is TP tending towards infinity, which is what we know, right? From physics, it's the quasi-static limit. Okay, textbook things. Now, with an active system, this actually starts to grow, and then I have a valley, a TP star. There's a finite protocol duration that minimizes the heat. Okay, already that's, if you were to sort of fall asleep now and just have this imprinted in your head, that's all the physics is there. You take the math and you just roll out the physics with this. So the target is, can we get this protocols at TP star using the response framework that I just showed you? And it seems that you can. So if I look at the heat, so on the left is the continuous and the discrete is the discrete heat. So this is the heat for the continuous system and the heat for the discrete system. Okay, fair enough. Now, what I do is I do expand all in Mathematica. Each term in the heat, I expand each term to second order, like I showed you. I expand each term, and then I massage it. Oh, no, that's not yet, sorry. Actually, without expanding it, you can massage both of these heats into this form, which is the first law of thermodynamics, right? The heat is equal to the change in internal energy plus the work. Now, if I don't have activity, so J is like, it contains signatures of the activity. If V is 0, J goes away. If epsilon, you remember this epsilon in the rates, if that's 0, J goes away, and we get the first law. We're back to textbooks, okay? So this J guy is going to play a big role, but we know we can go to safe ground when we kill activity. That's the main thing. That keeps us from not being stupid. Oh yeah, so this is what J is in the continuous case, and this is what J is in the active case. And that's just the protocol. Okay, very good. So what I'll do is I will expand this heat, and when I do, okay, oh God, I'm slowing myself down. So already we're in this, we have a form of the cost function that we know as optimal control theorists. So as a physicist, you might be like, oh, the heat is very arbitrary, blah, blah. But as a mathematician who's working on optimal control theory, well, this has the same form as the guy that we want to massage all the time. So already that's another motivation to look at the heat, right? Because it has all the ingredients of something that we want to massage. So let's go on massaging it. And we might learn more things, more general things about J. Okay, so when I've expanded the heat, I really get something like B, like a boundary term and an action term. And this is just what they are explicitly. This is the boundary term. It depends on these functions, which I can specify, but don't worry about it. The main thing is that this Lagrangian really looks like a Lagrangian. Okay, hopefully everyone, I don't know, recognizes this. It looks like alpha dot is the velocity, psi minus sigma prime is like a mass. So alpha is like a position, alpha dot is like the velocity. So it looks like a kinetic energy term. But I had a summer student who kept saying, oh, the energy. But I remember the Lagrangian doesn't have units energy, it has units power, right? Because it lives under a time integral of the heat. But V, and then there's a V, which is like an external potential, right? Oh, wow, or potential energy. Now, it just so happens that V, when you kill activity, V goes away, which is nice. This is just specifying the forms, but actually this is to show you that I spent so long talking about responses, but here they are. They enter this objective function. I need to compute the responses to compute the heat. Okay. I taught, so basically, okay, I want to extremize an objective function. As mathematicians, as physicists, you bring out Euler-Lagrange, right? Euler-Lagrange, knife and fork. You use that on this guy. And when you do, you always get some kind of differential equation. But here it's a nonlinear second order equation, which actually has the same form as an oscillator, so a pendulum, whose mass depends on position. That's supposed to be x. So if you have a pendulum with a mass that depends on where it is, and that's the dynamics.
What's the analogy with mass and symbol?
It's the upside minus sigma prime. Think of that as like somehow mass-like. Now, V prime is like a source term on the right-hand side. With activity, it goes away, and then I actually get back a very a great framework for controlling passive systems by David Sivak and Gavin Crooks. So this is Crooks from the Crooks fluctuation theorem, if people don't know. So we're back to safe ground, okay, not textbooks, but the papers 10 years ago, which are correct. Okay, so we're now on safe ground. And there's nice little surprises that because the Lagrangian is of this form, and it might be obvious to some, so sorry about that, but because the Lagrangian is of this form, I have a constant of motion, right? When my Lagrangian doesn't depend explicitly on time, if I do a Legendre transform, so people if that's the language they like, you do a Legendre transformation of your Lagrangian and you get a constant of the motion, which is the Hamiltonian. Now, in physicist language, I just rearrange and integrate. Now, on this oscillator, if I have, okay, you can see the problem a little bit. So V is positive, E is the Hamiltonian, but think about E as like how much I'm prodding. If I'm absolutely crazy and I'm just prodding like a crazy person, E is really high. But you can see that as E, oh god, it's a bit messy. So as E tends towards, and this is from above, as E tends towards the maximum of V, we have a problem, right? This blows up. Now, in the passive system, V is 0. I take out 1 over square root of V, and that's like finding the period of an oscillator, right? Okay, so there you go. This gives you the result. This gives you the optimal protocols. Okay. So I focused, as I told you I would, on mainly the framework and some of the subtleties. But you might still not believe me, right? Let's do the thing. And now, again, physicists are obsessed with toy models. We're like children, we have only one car, the Ising car, and maybe the trap somewhere. Okay, I stick an active guy in a harmonic potential. So the potential energy is half, Hooke's law, right? Put it on a spring. Now, if I change the strength of the potential, that's what's happening with alpha naught to alpha 1. Alpha naught is very, very flimsy. Alpha 1 is like strong guy. Forget B is more like the dynamical phase portrait, but the real thing is in C. So if I look at the trap strength from T equals 0 to the final protocol time, it looks like this. And it seems that there's two limiting curves for fast and slow. Now, for a passive system, all these curves would collapse onto one curve. So that's, okay, big lesson number 2. So in a passive system, you solve your control problem for 1 TP and you just scale it, right? You just multiply it by a TP. But here you can't do that. A lesson learned. Okay, the lesson is you have to do the control every TP. Okay, I've made people's lives harder, but this is what it is. I'm still thinking, so and there's some works of using machine learning. So this is smooth control that people have looked at using machine learning. So if you don't believe the response framework, then fine. But if you believe machine learning, okay. They found that actually they got protocols that look like this. Maybe that's hot and cold and so on. But they still span out like this. So this seems to be a general feature, but I haven't proven that it's general, so I'm left engineering, of controlling active systems. And I think the reason why is that you introduce another timescale. that we haven't yet understood.
As in basically the well of that graph you showed earlier, with the TP at the
Oh, yes, exactly. Exactly. Yes, good point. Good point. And this is just to show you that if I compute the heat from using response and I compute the exact one, which I can do in a trap, they agree up to the around the minimum. Okay, they shouldn't agree at low TP because that's when I'm driving fast and that's where response theory breaks down. So it's nice to be wrong when you know you should be wrong, right? Because then you're right a little bit. Okay. Now, there might be someone in the room who says, okay, it seems to not be totally weird. But a particle in the trap is trivial, right? It's one body problem, anyone can do that. Okay, well, what about a many body system, particularly the one I showed you about the experiment? If I shine light on these guys, they come together. So I can make a model of this, this is the car, it goes vroom, this is the dynamics. It has some orientation that's specified by here, and they bump heads. It doesn't matter how they bump heads, as long as they bump heads, okay? Then you get these clusters. Okay. Now, the nice thing about control from the left one is I'm going from particles that are small and I'm blowing them up like balloons. And then they start to clusterize. And then on the right, I'm doing the opposite. They're going from big balloons and I'm shrinking them. The main physical thing is that I'm changing the packing fraction, right? That's it. It's just that's it. Okay. Now, one subtlety is that, so the left is, the phase is a homogeneous phase. I have particles, they're in the box, they're distributed homogeneously, but they're still active, they're still producing entropy. Now it seems that all the protocols collapse onto a straight line and one line, right? So I thought, well, this means that it can't be because it's active. But in the cluster case, I really see this fanning out. Now I know that if I zoom in on this straight line, there has to be some fanning out because it must be because of the entropy production. So if I zoom in, so you can see this axis, right? Very small. I do get fanning out. And then, of course, it's just a one-to-one. So that basically teaches you that the presence of activity, you get this fanning out of the protocol. This is just the heat. Okay, I can get the minimum. That's just the lesson. Okay, so it looks like I'm in good time. And hopefully we can stay for a bit of questions. I don't mind staying, if that's okay. If people want to go, please go. So I think to conclude, I've hopefully shown you that just thinking about and quantifying the response of an active system, you can begin to systematically control it. There's some lessons to be learned when comparing directly to the passive systems. We've extended this to discrete state systems. Another thing is that the discrete state case is thermodynamically consistent, but the continuous state models, sometimes they're not actually, right? So maybe people can think about that. If you're obsessed with machine learning, well, if you want to test your machine learning, you can inject, the protocols resulting from this framework, and you can almost feed it to your machine learning framework to give it a head start or not, right? But the key thing is this is a machine learning. I didn't show you any machine learning today, so maybe that's a good testing ground. And Michael mentioned at the beginning about phase transitions. A future goal of the field is to optimally drive through phase transitions, which is notoriously hard, even to think in passive systems, because you have, like you said, correlation lengths get larger, you get something called critical slowing down. I think some progress can be made towards this, but we're stuck. So new ideas are here needed. And oh yeah, just to say that so the co-authors are Karel, who's now at the Niels Bohr Institute in Copenhagen, and Etienne, who's in Luxembourg. And yeah, next year I'll be in Edinburgh. So yeah.
Questions?
No worries.
And something I was thinking, you write down a Lagrangian where you have the control of the function alpha, and then you said you derive the Euler Lagrange equations, and then you sought to get the optimal possible alpha. Could you do it? Did you try to do it with contrarian maximum principle? Can you do it? There's some limitation given that you're using response theory, maybe on the fact that this is a perturbative approach since you're expanding around certain state.
Yeah. So from what I believe, Pontryagin, I mean, it might essentially be calculus of variations anyway. I think ultimately you have to invoke Euler Lagrange at some point. I think it's the same thing. I think the Pontryagin principle is just saying that the optimal thing to do is to extremize J, and you do that through calculus variations. So you will end up with the same equation. But in some cases, you can do things like invoke Lagrange constraints on the objective function. You can do things like dynamic programming, and that's more optimal control flavor, without doing response, right? Yeah.
Okay, because I was curious, I think that I'm with pedestrian or optimal control.
Well, same physicist.
That Pontryagin also works, but you need to have the control in a given interval.
Yes.
Which is also what leads to bang-bang protocols if you have linear systems. Whereas in your case, it's perturbative, maybe you don't have this boundedness.
But you mean in time or like?
No, on alpha, on the magnitude. Your alpha shouldn't be too
Yes,
strong
true,
in your
yes.
perturbation, correct?
Yes, it shouldn't be too strong. Yeah, no, that's true. You mean like you impose the bound, but not from response?
Exactly.
Okay, yeah, I didn't think about this. Yeah.
So in the second example, where you basically had a Brownian motion on the angle.
Here, yeah. Yeah. No. It's a good point, actually. So, okay, I mentioned to make something active, you have this self-propulsion, and there's choices to impose that. In the first case, I used something called, I didn't show it, but Ornstein-Uhlenbeck processes, which are malleable to analytical treatment. And when people simulate many-body active matter, this is the usual thing they do. And this was just to show that it doesn't depend on a particular implementation of activity. It was like, we can also do it with this thing, and to show that it doesn't depend on how you impose activity. Because actually, this is normally very weird to do analytical stuff with. This particular way, right? I mean, Ornstein-Uhlenbeck, you know the two-point function. You can use Wick's theorem or Isolus's theorem in maths or whatever. So, yeah. Yeah, okay, that's the, so there's a deep question, I think, that, I don't know if Sam was asking, but that, so Sam, he's brought up a deep thing, right? That if you've noticed, what I've done is I started from the microscopic picture, the equation of motion for one particle. I could have started from the equation of motion of the distribution, which is the Fokker-Planck. Right. Now, in active systems, it's not known what the steady state is, right? So if you can find a trajectory to do things without, I think you run into some trouble. There's ways to do it. So in optimal mass transport, that's what you do, right? You massage a distribution to go from this form to another form. And there you actually need to work with things that have a well-defined non-equilibrium steady state. But actually that's another problem. How to deal with that, actually. That's a good point, actually. Yeah. Yes, this is 1D.
In this case, you're not just changing the angle, right? You're allowing the active
Particle, yeah.
to change in terms of magnitude as well.
Yeah, so the particle's moving in one dimension, and alpha is really like, it's just the strength of the trap, yeah. So it's 1D. Yeah.
I can repeat this question, but I had something related to something.
Yeah.
Related to maybe to what Sam was alluding to. In something, do people ever do things where you have some sort of bias that wears off? Do people ever do things a little bit like this? And help you with if you have like a heavy toe and need some from the top, but you don't want to spend all your time going in that direction.
It depends how you think about it. It depends on what you count. Like annealing is in some ways. We can get into that.
So annealing, you're saying like you have some Hamiltonian, you have some reference, and you have some bias, right? That you know the bias, but you remove it. A bias over time, and then you somehow account for that bias at the end.
It just wears off.
So it like
You can do it in
Something like that.
like it wears off with time or something or whatever. Okay. Well, I've never thought about it like that. I think in general you have, I guess here you have a reference Hamiltonian, which I guess would be the passive case, and you have some delta on that, which in my case could be an activity. And Monte Carlo, you impose that, right?
So another question I had is,
Yeah.
this might be really obvious, but I find it quite interesting you had two limiting curves, the slow and the fast. Is that something you expected?
No.
Okay.
I think I actually thought it was wrong, to be honest. I think now, we're trying to, so with Corel, we're trying to understand, like, put a finger on the nose of why exactly that's the case. Another thing is that, well, this is a conjecture that if you have a system with multiple timescales, does this cascade through here? So do you have, instead of, you have 3 limiting cases if you have 3 timescales? Because you think about what you're doing is that as you approach a relevant timescale in the physics, the protocols might bunch up. There might be some regime that you can collect. This is speculation.
So, can you use this framework if you don't have the running cost? You just have the initial endpoint.
Yeah. It's super easy. Yeah.
So the minimum you get there, is that because you're considering also the energy consumption of the active particles themselves?
Yes. Yes, so this is a good question because what I've discussed with a few people is that basically, okay, what I've done is I've accounted for the heat through looking at the work done on the particles to the environment. Systematically, just account for that. But Francesco's hinted to the point that each particle has a background of activity that I could do well to just take that away. And in some cases, the heat will not have this minimum, but in some cases, like in a discrete case, you still see this actually. Maybe it's the way we've imposed activity, but it's not trivial that you can completely get rid of this by taking away the housekeeping heat.
But the large time behavior is linear.
The large time behavior is always linear with activity in some sense. This is guaranteed. This is guaranteed. Yeah.
That linearity, what means that you stop at the second term of your expansion? That's what I was going to say.
Not necessarily. So the linear term, a little bit. Yeah, it's not. Yeah, it's not completely that, but yeah.
Is it a constant dissipation rate given the central function, which dominates?
Yeah. So actually, the reason why I didn't show it, but in the paper I didn't show it here, did I? Okay, so what you would do is if V, sorry guys, V is the self-propulsion. This is J, right? If this V doesn't depend on the protocol duration, right? Like you will digest your lunch, even if I'm moving you around, right? So I can when I integrate J, I get a factor of TP. It doesn't depend on T. That's the same on the protocol T. So I get a factor of TP, and I can bring that out, and then I have something linear in TP. That's in a continuous case. That's the obvious linear regime. In a discrete case, you have to massage a little bit to get this, but you always get this. Yeah, thanks.